Okay, so on this first one here, we're going to use the common denominator, which would be 6, and what we can do is we can multiply everything by 6. Alright, so I'm going to multiply each term here by 6. If I do 6 times w over 3, so I do 6 times w over 3, what's going to happen with the 6 and the 3?
Reduce.
It's going to reduce to what?
1. The 3 becomes a 1.
The 3 becomes a 1, the 6 becomes
2.
a 2. So really it reduces to 2, right? So we have a 6 on top, 3 on the bottom. That just reduces to 2. So it's going to be 2 times w, which is
2w.
2w. Now, did everybody follow what just happened there for that first term? Do you want me to write it off to the side? So 6 times w over 3. The 3 and the 6 cancel. They reduce, and we get 2w over 1. But anything over 1 is really just itself. So we get 2w there. Does that make sense? Okay. How about 6 times 3 halves? So when I do 6 times 3 over 2, what's going to happen with the 6 and the 2? They're going to cancel. What's going to be left? 6 divided by 2 is 3, and then multiply that by the 3 that's there, and we're going to get 9. So on the left side, we get 2w plus 9. What's going to happen with the 6 here and the 6 here? They cancel out completely, and we just have 7. Now, isn't this equation a lot easier to solve than this one? We could have, if we wanted to, probably at first glance, we might have thought about doing this. We could have subtracted 3 halves from both sides, and then multiply both sides by 3, and we would get the correct answer. The problem is we're working with fractions a lot, and it's easy to make mistakes when you're working with fractions. So we have 2w plus 9 equals 7. What do I do next? Okay, so we'll subtract 9 from both sides. So this is something called the addition property of equality, which essentially says that we can add or subtract the same thing to both sides of an equation. We get another valid equation. The 9's cancel each other out here. So we end up with 2w equals what? Negative 2. And let me copy that up top. Oop, that's not what I wanted to do. Alright, so we have 2w equals negative 2, and what do we do last to get w by itself? Chris? Okay, so we'll divide by 2. This is what's called the multiplication property of equality, which says we can multiply or divide both sides by the same thing to get another valid equation. We get w equals negative 1. I was giving Stephen a little trouble earlier. If you just write down an answer, I don't know if you got that answer from the person's paper next to you, if you did it by doing it in your head, if you did it by doing it in a calculator. You need to show me something that shows you know what you were doing and you know how to get the answer. So on every type of problem we do, if there's any work to show, you need to show it, even if it's something that's pretty simple and you can do it in your head. You need to be able to communicate to me that you know what you're doing. Terrence, question?
Last year I had this girl, she said like when you like do the problem on top, like you like circle the equal signs and like once all the okay. Like what I did, I made them all common denominators with 6, and then when I did that, I crossed out all the denominators, and then that gave me
Okay, good, and that's what you were saying too, right? So if you make them all have a common denominator of 6, once you do that, then you can just get rid of the denominators. You can just clear those out. So just we'll start that way here. Let's say we want to make w over 3 with 6 in the denominator. We would multiply by 2 over 2, and we get 2w over 6. Yeah. And then here we would multiply by 3 over 3, so we would get 9 over 6. And here the 7 over 6 just stays. And then at that point, we can just get rid of the denominators, and we have 2w plus 9 equals 7. And that's the same thing we had. Is that what you're saying?
Yeah.
Cool. I like that way. Okay, any questions about that one? All right, next one. We had y squared minus 4y minus 45 equals 0. Obviously, we want to solve for y here. Who thinks they remember how to do this? I know Emma did. I saw that. You remember? Can you tell me what to do? No. I need to know how to do it.
Well, I got y plus 5 and times y minus 9 from
Perfect. So what we're doing here is factoring, right? So what we're looking for are two numbers that multiply to get negative 45 and add to get negative 4. Those two numbers are going to be a positive 5 and a negative 9 because 5 times negative 9 is negative 45 and 5 minus 9 is negative 4. Okay, so we factor it. And then what are we going to do after we factor it?
and then y plus 5 equals 0 and then same to y.
Perfect. So then we can set each one of these factors equal to 0, and they will give us a different answer for y, a different value for y. So the first one we get y equals negative 5, and the second one we get y equals 9. Now you may, when you were solving these equations last year, you may have noticed a pattern. The solutions, the answers for y, the negative 5 and the 9, are always the opposite of what you have here, right? So if I put a negative 5 in for y, that's going to make this factor here 0. If I put a positive 9 in here, that's going to make this factor here 0. Okay, and it's always going to be the opposite of the number that's in there. Okay, any questions about that one? How many people got that? Okay, pretty good. You're going to have to remember how to factor. We are going to do a lot of problems this year where the geometry will give you the setup for a problem, but then you're going to have to use some algebra to actually get the solution. Question? Or you want to help me out?
Come up with one solution.
Both. Terrence, you want to help me with this one? Okay, what are we going to do here, Terrence?
Multiply the stuff on the left by 11, and then the stuff on the right by x minus 2.
Okay, so what we're using here, anybody remember what it's called? It's called the means extremes products theorem. Does that sound familiar? Basically what we're going to do is we're going to multiply both sides of the equation by 11. So we multiply by 11 here, and we multiply by 11 here. And the 11s over here cancel, right? Yeah? And then, as Terrence suggested, we're going to multiply both sides by x minus 2. And I'm not going to write it over on the left side because I'm a little out of space here. But the x minus 2, well, I could squeeze it in. The x minus 2 here, and times x minus 2 here, the x minus 2's over here are going to cancel. So what ends up happening is we multiply the bottom right, the 11 times the top left, and we multiply the bottom left times the top right by the time everything cancels out. So what we have is 11 times 12 equals 6 times x minus 2. Okay? Can you help me simplify that, Terrence? What's 11 times 12?
132.
Okay? And what's 6 times x minus 2?
6x minus 12.
Oh, okay? And then what?
Add 12.
Add 12 to both sides. So we get 144 equals 6x. Then what?
Divide on the 24.
Okay, good. Let me give myself a little more space here. I'm just going to make that smaller. Okay, so then we're going to divide by,
Oh, 6.
yep, so divide both sides by 6, and you get x on the right side and 24 on the left side. Cool? So I call this the means extremes products theorem. You may have learned in the past something else that you could call it. Anybody ever heard of cross multiplication? Okay, that's basically what we're doing here. We're cross multiplying. So we multiply the 12 times 11 and the 6 times x minus 2. And the reason that works is because when we multiply both sides by 11, the 11s cancel over here. When we multiply both sides by x minus 2, they cancel over here. So we end up cross multiplying. All right, and last one. This is my favorite one. What are we going to start with here? What should we do first? Chris?
Cancel the 2 and 18.
Okay, we could do that. We're not going to though. Actually, I'm sorry. You can't do that
Why not?
because they're not being divided by each other. They're actually going to end up being multiplied by each other. So you cannot cancel the 2 with the 18. If they were on the same side of the fraction, or I'm sorry, the same side of the equal sign, you could. We're going to start the same way we started the last one, which was by doing what? Cross multiplying, or means exchange products. So what we're going to do here is we're going to multiply both sides by z minus 9, and we'll end up multiplying those two together. What is z times z minus 9? Z squared minus 9z, okay. And then we're also going to multiply both sides by 18, which we're going to end up multiplying those two together, which will be what?
36.
So we get z squared minus 9z equals 36. Who knows what to do next?
You subtract 36.
Okay, good. We want to set this equal to 0. So we're going to subtract 36 from both sides. We get z squared minus 9z minus 36 equal to 0. And then what?
And then you separate it, which is z plus 3 times z minus 12.
Perfect. So again, we're going to factor here. So z, what would you say, plus 3?
Yeah.
And z minus 12.
Mm-hmm.
And we'll set each one of those factors equal to 0. From the left factor, when we say z plus 3 equals 0, what do we get?
-3.
Z equals negative 3. And from the right factor, z minus 12 equals 0.
Positive.
We get positive 12. And you guys thought you got out of algebra class. How do you guys feel about this stuff?
Don't like it.
Don't like it? Well, unfortunately, like I said, a lot of the geometry that we're going to do is going to allow us to set up an algebraic equation, which then we'll have to know how to do the algebra to solve. So we'll do some reviews from time to time when we're getting close to problems where you'll have to do this. We are going to be coming up on a topic called similarity. And with similarity, you're going to have to solve proportions. And in a proportion, you solve by doing exactly what we did here. You solve by using means exchange products or by cross multiplying. All right. Any questions about any of that? Okay, so that's enough of the opener. How are each of those things, points, lines, and planes, represented in this picture? So let's just go one at a time. How are points represented in this picture? Sebastian, did you say something?
No.
Oh, I thought you did. Did he say something? Oh, okay. Look at this picture. Where do you see points? Say that again, Emma.
The dots.
The dots. So in a picture, we typically represent a point with either a dot, or in this picture, they're actually represented as little circles, but the points are just dots. So I said yesterday we don't define a point as a dot, but we represent a point with a dot. So these are all of the points that are depicted in this picture. How are the lines represented in this picture? With lines, right? And what did I do in the picture to show that they're lines and not line segments?
You put arrows at the end.
Exactly, I put arrows at the end. So lines are represented here with lines, and then put arrows at the end to show that they go on forever. And then how are the planes represented? Because a plane is not really easy to draw. The idea of a plane is it's a flat surface that goes on forever in all directions, and I can't really draw that. So how do I draw it in the picture? Okay, so there's two planes up here. What do they look like? What's that? Okay, so the combination of the two look like a cross, but just any one of the planes. Look at the shaded gray plane. How did I draw it? What does it look like?
Square.
It kind of looks like a square in perspective, or from our perspective, it looks like starts with a P. Parallelogram. Okay, you guys remember what a parallelogram is? So typically we draw a plane as a parallelogram, and a parallelogram is really just a square or a rectangle that looks like it's laying down a little bit. Okay? So we draw a plane as a parallelogram. It looks here in this picture like, sorry, let me get my pen here. It looks like the plane has a border, and we have to draw it so that it looks like it has a border. Otherwise, if we don't, you're not going to really even see it. You're not going to see that it's there. So if we truly had that plane extend off forever in all directions, we wouldn't be able to see it because there would be no edge to it. So we draw planes as having an edge, but we do assume that it goes off forever in every direction. So this plane really doesn't stop at the edge that's drawn here. It keeps going in all of these directions. Okay? Does that make sense? So you could picture it's a flat surface. It almost looks like maybe a piece of paper or a desk, but then that piece of paper or desk could be extended off in every direction. To draw it, though, we draw it as a parallelogram. All right? So let's answer some questions here. I'm going to ask you to do a few things. First of all, I want you to name each line in the drawing. How many lines are in this drawing? 2. I want you to name each line in the drawing at least 2 ways. And actually, I'm going to change that. I'm going to make it 3 ways. We can name each line in this drawing 3 different ways. Who can give me one? One way we can name a line. Chris? Okay, we could do that, except remember yesterday, what do we need to name a line? Look at your notes from yesterday if you forgot. How do we name a line? We could call it line ABG, but it's really more than we need, and I don't want to do that. Emma?
With that lowercase letter?
Okay, we could use lowercase letter. That's not what I was getting at, but that'll work. So we could call it line M. And I'm looking here at this line right here, since that's where Chris started. AG would work. Okay, so what we really want is just 2 points on the line. And then we'll use the line symbol. So we could call it AG. What's another name we could call that same line? This one actually has 7 different names. Chris?
GA.
Okay, we could call it GA. Terrence?
DC.
You're looking at a different line. Let's stay with the same one for now.
Oh, okay. AB.
AB, okay. What's another name for it? Okay, we could call it BA. There's actually 2 more.
BG.
BG. Or flip that and we could call it GB. So this one line right here has 7 different names based on the points that are on it and then the lowercase letter that's with it. All right, how about the other line? Are we going to be able to name that one 7 ways? No, why not?
There's only 2 points.
There's only 2 points on it, so that's going to limit what we can do here. So we want to name that line. Who can name it one way? Emma?
E.
That's actually an L, but yeah.
Oh.
Okay. Somebody else. John?
DC.
Okay, we could call it line DC. Remember to use capital letters. Remember the line symbol. And Amani? CD. Amani, that's not a jacket, is it? You're not supposed to have jackets. Any other ones? Could I call it line CL? No, that's mixing different ways of naming it. If I'm going to use 1 point, then I need to use another point also. And L is not a point; it represents the entire line, so that's not good. All right, so those are the 3 ways we can name that line. All right, moving on. Which points in this picture are collinear? Now, I kind of tricked you at the end of the day yesterday, and I gave you 2 points, and I asked if they were collinear, and there was not a line drawn through them. And it turned out that those 2 points were or were not collinear. They were. Any 2 points are collinear, right? So it wouldn't be useful for me to say, okay, E and F are collinear, D and B are collinear, A and G are collinear, D and B are collinear. I think I said that one already. That would be kind of pointless because we know that any 2 points are collinear. Let's pick 3 points. Who can name 3 points that we know are collinear? A, B, G. How do you know that they are collinear?
Because of the line of them.
Yeah, there's a line that goes through them. Okay, Terrence?
I have like a different question about coplanar.
Coplanar.
Yeah, like
We'll get there.
oh, we still have
Yeah, collinear. Do you see any other 3 points that are collinear?
D and C.
That's only 2 points.
Oh, we gotta have 3. We got 3 points. Oh, I don't know. Because
Darwin?
you go the other way and put G, B, A.
D, B, A?
G, B,
G, B, A. Okay, they're still the same 3 points though. Yeah, we could go the other way and list them in a different order. But they're still the same 3 points.
A, C, F.
What do you guys think? A, C, and F. Oh, that's not a very straight line. Are they collinear? Remember what we said yesterday, don't assume. If there's not a line going through them already, don't try to draw your own because it may not quite be accurate. We're just going to say they're not. So the only points in this picture that we could say for certain, the only set of 3 points that we could say for certain are collinear would be A, B, and G. Okay? Moving on. There we go. Name a pair of opposite rays. There's really only one set of opposite rays. So let's refresh first. How do we name a ray? Darwin? Okay, so the ray symbol is like a line segment, but it has an arrow on one end. So how do we name it? Like a line, we use 2 points, and then we put the line symbol above it. How do we name a ray?
The point of the ray and then the other point on the line. And the
Okay, good. So we have to name the end point first, and then another point on there. So looking at this drawing here, does anybody see any opposite rays? A couple people do. Where are they?
B, A, and B, G.
Okay, good. So BA, so this we'll call ray BA, and that would be the ray starting here at B and going toward A in that direction. And then, what was the other one you said? BG. Ray BG would start at B and go in the direction of G. And those 2 rays put together form a straight line, so those are opposite rays. Notice that the opposite rays both start with the same letter. Since we always use the endpoint to name the ray first, then we're always going to have the same point first when we have opposite rays. Are there any other opposite rays in the picture? No. In fact, we couldn't have any more because we didn't have any 3 points that were collinear besides those. Okay. Name each of the planes in the drawing in at least 2 ways. So let's start with the vertical one, the white plane here. What's one way that I could name this plane? I'll shade it in here. What's one way that I could name this plane right here?
H.
Okay, good. So one way to name a plane is just a bold capital letter. Now it's kind of hard for you to write in bold. You could double it up maybe if you want. But we could call that plane H. Alright, what would be another way we could name that plane? Let me get this scribble out of your way here. What do you think?
ADF.
ADF? What do you guys think about that? Are all 3 of those points on that plane? Is A on the white plane? Is D on the white plane? Is F on the white plane? So they're all 3 on there, right? Are they collinear? Because we said it has to be 3 non-collinear points. Are they collinear? No. So we're fine. That would be a good name for it. We could call it ADF. In fact, we could take the ADF and we could rearrange it and we could call it plane AFD or DAF or DFA or FAD or FDA. Any one of those 6 would have the same essential meaning. Could we use a different combination of letters for that plane? What do you guys think about ACF? Could we call it plane ACF? Do you want to just not think about it? Terrence, what do you think? Okay, it would be, I would avoid it. It actually technically would be okay because earlier we said those are not collinear. And since there are 3 non-collinear points, that would be okay. I would avoid it though because they look like they could be collinear. And if for some reason later on it turns out that they are, then there's going to be more than one plane that goes through those 3 points. So even though we said they're not collinear, I would avoid it because they're close. In general, when we say non-collinear points, we want to use points that look like they make a triangle. So if I draw the lines that connect those 3 points, A, D, and F, it very clearly makes a triangle in that plane. So that would be a good option for a name there. Okay, how about the gray one? Let's name the gray one real quick. At least one way. Steven? The horizontal plane, the flat one.
You call it ECB.
Okay, ECB. What do you guys think? Would that be acceptable? Yeah, all 3 of those points are on that plane. It doesn't matter that C is actually on both planes. That's okay. As long as those 3 points are all on that plane and they're not collinear, they're not all in a straight line, then that would be good. All right. Could we have used the point D also? Yeah. What if I said plane, and I'm going to add another point here. What's the GH? I'm going to use point I here. What if I called something plane CID? Would you know which plane I'm talking about? Why not? Because all 3 of those points are on both planes, right? So you don't know in this picture if I'm talking about the vertical plane or the horizontal plane. And that's why we can't use points that are all in a straight line, because they could be on more than one plane. Does that make sense? Mm-hmm. Okay, moving on then. What does it mean for 2 objects to intersect?
And they go through each other.
Okay, when they go through each other. Yep. John, you want to add to that?
When like 2 lines eventually end up meeting at one point.
Okay, could be. It doesn't necessarily have to be 2 lines. So the next question you can see there, we're going to talk about how 2 lines could intersect, or a line in a plane, or 2 planes. The typical intersection that we probably think about it, at least in geometry, would be a line intersecting with another line, and the intersection of those 2 lines would be, you guys both suggested it here, it would be that point right there, right? So the intersection of 2 lines could be a point. What it means is that that point is shared by both lines. So the intersection of those 2 lines is that single point, because that point is the only point that's on both lines. All right. With lines, it's pretty simple. What ways could 2 lines intersect each other? Is it possible for 2 lines to intersect at more than one point? So we have a line, and then we have another line, and that other line intersects at more than one point. Is that possible? Not really at 2. Could it intersect at like infinitely many points? Say like that? Do you see what I did there? They're laying on top of each other, right? So since every point along the way, this point here, this point here, this point here, every point on one line is also on the other line, they actually intersect infinitely many times. You may argue that they're really just the same line and they're not 2 separate lines, and that would be a fair argument. But if we consider them as 2 different lines, then their intersection would be infinite. So we could have 2 lines that intersect at one point, like we have up here, we could have two lines that intersect infinitely many times. Is it possible that two lines don't intersect at all? Yeah, what would that look like? Yeah, parallel lines, right? So that line right there that that I've got, and this line right here, if I extended both of those lines forever, they would never intersect. Okay, that's kind of the idea of parallel lines. There's actually another way that lines could look and never intersect. The problem is we can't draw it on a piece of paper. So actually I'll use the room as an example. The top corner of the room up there. So where the front wall meets the ceiling, that's a line. You guys agree with that? Okay, another line in this room would be the bottom corner under here, under the computers, where the side wall meets the floor. Okay, so we have a line up there, we have a line down there. Are those two lines ever going to meet?
No.
Are they parallel to each other? No, one of them's running out that way toward the football field, the other one's running out that way toward Millstadt, and they're never going to meet, but they're not parallel. Do you know what they're called?
I don't know what they're called, but it's basically two lines in a three-dimensional way.
Yes, exactly. It has to be in 3 dimensions. This is not possible in 2 dimensions, like on a piece of paper, which is why I said we can't draw it. It would have to be 3-dimensional. So there are lines that don't intersect, but they're not in the same plane, so we can't draw them on a piece of paper. They're called skew lines. On a piece of paper, the way we would draw skew lines would be like this. We'd draw one line and then show that the other one is not in the same direction but kind of jumps over it. Obviously it's not a line, but it's our way of showing that they're not intersecting there. Okay? So we can't accurately draw skew lines because it has to be 3-dimensional, as John said. And just for your own good, this is not a term that you're going to have to know. Oh man, my internet's being slow, sorry. It's coming up slowly. This is how you spell skew, in case you are wondering what is that weird word that Mr. Betts is saying. Okay, so that's how two lines could intersect. How about a line and a plane? So let's say I have a plane. We'll use the chalkboard as our plane here. And I have a line. I'm going to use my ruler as my line. Okay, this is a meter stick because it's 1 meter long. So in what kinds of ways can my meter stick here intersect with my plane up here? Is it possible that they intersect at one point? It is. Can somebody describe what that would look like? John?
Wouldn't it be like the line intersects with like the edges of the plane?
The plane doesn't have an edge though. Like this one does, but let's pretend like it just goes on forever. For this to intersect that at one point, it might look something like this. Okay, so it's touching at one point, but it's going to go through and it's going to go beyond it. So the one point of intersection is right here where my hand is. Does everybody see that? And it could be at an angle like this too, and it would still intersect at just one point. Is it possible for this to intersect that plane at exactly 2 points? No. For the same reason that we had earlier with the lines. If it comes out at one point and then goes back in, it's going to have to curve, right? What about more than 2 points? Could it intersect infinitely many times? Yeah, if I just put my ruler on the plane, then every point on the ruler is on the plane and there's infinite many intersections, right? Does that make sense? How about never? Is it possible for this, or the extension of this, to never intersect this or its extension? What would that look like? John?
Where it's like going that straight down and not reaching it.
Yeah, parallel to it. Okay, we still call it parallel, and it could be at any direction here, as long as their extensions are not getting any closer to each other. So the intersection of a line and a plane are actually very similar to the intersection of two lines. Okay, now the last one we're going to talk about, and this might be the hardest one to visualize, would be two planes. I'm going to use my iPad as one of them, and I'm going to use, again, the screen here as the other. Is it possible for this iPad and the screen and their extensions to never intersect? Darwin? Like that? Yeah. I mean, if this lays flat here, they're an equal distance and we extended them, they would never intersect. So basically they're running in the same direction. They're called parallel still. Okay? Is it possible for them to intersect at just one point? Like this. Could they intersect at just one point right here? Think about the extension. What's going to happen, Darwin? Yeah, this plane here is going to keep on going right here. And not only is it going to intersect there, but it's also going to intersect here, and all the way over here, and all over here. And really that intersection is going to be a what? A line. So the intersection of a plane and another plane, if they intersect like that, is going to be a whole line. And that's the main intersection that we're interested in. Think about this one, the front wall and the ceiling. We already talked about that, right? Where the front wall and the ceiling meet, what is it? Up in that corner. What kind of shape is that? Starts with an L. Rhymes with wine. Line, yes. Okay, so where the front wall and the ceiling meet, it's going to be a line. And then the obvious one then is if they're just laying on top of each other, they share all their points. That would be an infinite intersection. All right, so I've got a worksheet for you here. One of the questions I'm going to ask you is, what is the intersection of two planes? So like down here, if you're looking at this picture down here in the corner, where that gray plane and the white plane intersect is what kind of shape? Where the white plane and the gray plane intersect, what is it? Starts with an L. It's a line. Okay, it's the line right here. So where those two intersect is that line. Keep that in mind.